Well, this is a discussion about the derivatives of the trigonometric functions other than sine x and cosine x, because we've already discussed that the derivative of sine of x is equal to the cosine of x, and the derivative of cosine of x is equal to sine x. Be real careful, excuse me, not sine x, but negative sine x. That's a little bit hard to read there, so make sure we recognize there's a negative sine x in this case. So we want to look at the other trig functions. That's the derivative of tangent of x and the derivative of cotangent of x, and likewise the derivative of secant of x and cosecant of x. Well, we'll first look at the tangent of x. The derivative of tangent of x, the first thing that we'll recognize is that we can write tangent of x as a quotient, sine of x over cosine x. And being a quotient, we can use the quotient rule. And of course, the quotient rule would be take the denominator times the derivative of the numerator, and so on. So let's look at what we get when we use the quotient rule. We see that we'll take the denominator of the quotient here times the derivative of the numerator of the quotient that we're writing here, and then of course minus the numerator of the quotient, sine of x, times the derivative of the denominator. And then of course we divide all that by the denominator of the quotient squared. There's our square. Now let's go in and calculate each of these, because we know the derivative of the sine of x is just cosine x, and we know the derivative of cosine x is just negative sine x. So in our next step, let's see here. In our next step, we see that we've actually filled in derivative of sine of x being cosine x, and derivative of cosine x, of course, being negative sine x. Now, we recognize here that we really have cosine x times cosine x, which we write cosine squared x. And here, negative times negative will become positive sine squared x, as we see that I've got written below here. Now, we might stop at this point. Oh, and by the way, notice, of course, I rewrote cosine of x all being squared as in the normal fashion cosine squared x. So here we have cosine squared x plus sine squared x all over cosine squared x. And we need to be careful to recognize things like this. This is one of the toughest elements that we deal with in calculus or any math class, is to recognize information that we know, but we are not thinking along those terms because we're working on a different type of problem. But we remember that one of the main identities from calculus is sine squared x, or theta, whatever the variable is, sine squared x plus cosine squared x is equal to 1. Now this isn't written in that order, but because of the commutative property of addition, this is exactly the same thing as sine squared x plus cosine squared x. And so we have nothing more than a 1 in this position. So we consider replacing that with a 1, and when we do, of course, this fraction becomes 1 over cosine squared x. And then again, we may, because we're not thinking in terms of trigonometry, we're thinking in terms of calculus, but it's important to recognize that since secant of x is 1 over cosine x, then 1 over cosine squared x, of course, is secant squared x. And of course, this is the result we're really looking for. We're really looking for the fact that what this is, remember, is the tangent, the derivative of the tangent. So let's go in and reset our forms here. We know now that the derivative of the tangent of x is secant squared x, and that's an important result. We could have done the same type of analysis when we calculate the derivative of cotangent of x. After all, we could write cotangent of x, couldn't we, as we could write cotangent of x as cosine of x divided by sine of x. So when we're trying to calculate the derivative of cotangent of x, we would really just be calculating the derivative of this quotient, and of course we would use the quotient rule again but of course we get a little bit different result. And of course in the case of secant of x, we could write that as 1 over cosine of x. So here we really have the derivative of 1 over cosine of x, and in this case we could also use the quotient rule. It's just that the numerator would be 1, and somewhere along the way when we took the derivative of the numerator we would get a 0 in part of our calculations. And similarly here we could write cosecant of x as 1 over sine x and use the quotient rule in this case as well. Well, if we were to go through each one of those, the results that we would see would be that the cotangent of x results in negative cosecant squared x. Now be careful again, there's a negative sign right here as there was in this position. And we find that the derivative of the secant of x happens to be secant of x tangent of x times tangent of x. And similarly, the derivative of cosecant of x happens to be negative cosecant of x cotangent of x times cotangent of x. Now before we leave this, I would like you to, you're going to be responsible for knowing each of these derivatives. And the real point probably would be that you need to notice the similarities or somewhat the relationship between the derivative of the trig functions and the derivative of their cofunctions. These are the cofunctions. Cofunction of sine is cosine, cofunction of tangent is cotangent, and cofunction of secant is cosecant. Well, it's going to be important to memorize these three. Okay, if you memorize these three, then you see the similarities over here. Of course, each one of them has a negative sign, where the derivative of tangent of x is secant squared x, where the derivative of cotangent of x is the opposite of cosecant squared x, as you see. And you see the same relationship here. Derivative of secant is secant times tangent, but the derivative of cosecant is negative cosecant times cotangent. So if you focus on memorizing these and remember these relationships, you can quickly have all 6 of these memorized. Well, we'll look at an example here next using our new information. In this example, we're asked to find a second derivative. That's a little hard to read, f double prime of x, given the function f of x is secant x. So we begin, of course, to find the second derivative, we need to know what the first derivative is. So we begin with the first derivative, and the derivative of secant of x we just discussed, and we're in the process of memorizing, is secant of x, secant x times tangent x. Well, once we visualize the first derivative, we know, of course, to find the second derivative, we'll take the derivative of the first derivative. And in this case, we notice we have a product of functions that we're taking the derivative of, and so we have to use the product rule to write this down. So let's remember what that product rule is, and let's remember that that's what we're doing here. So we're going to use the product rule at this point. Maybe you can work ahead of me. Okay, well, the product rule tells us that we take, of 2 functions, we take the first function, which is secant of x, and we multiply that with the derivative of the second function. So we need to multiply it with the derivative of tangent of x. And maybe we have that memorized, maybe we don't yet. So we need to make sure that we know how to write down the process that we're going to use. we need to be able to look up the derivative of tangent of x. So here we go again. To take the derivative of a product is the first function times the derivative of the second, and then we add to that the reverse, that is the second function, tangent x in this case, times the derivative of the first function. And once again, we need to worry about and practice on how we write down what we're proposing to do, because at this point we don't have all these derivatives memorized and we have to pause and go figure out what that is. Okay, so we're ready to continue though. Once again, first function times derivative of second plus second function times derivative of first. Now, we just discussed also, or we can look up, that the derivative of the tangent function is the secant function, the secant squared, pardon me. So we have we have in this case the secant x and the resulting derivative of tangent x, which is secant squared x. And of course over here we have tangent x times the derivative of secant x. And we've already used that idea once. Remember, the derivative of secant x is secant x times tangent x. So in this position we have our tangent of x and then our resulting derivative of secant x, which is secant x times tangent x. About out of room over there. As we look through, we notice here we have secant x times secant squared x, which of course is secant cubed x. And in this expression we have a tangent times a secant times a tangent, so we actually have secant x times tangent squared x. And we may leave our answer this way. We may be tempted to look in the back of the book and see what the answer is, but we do also notice that we have a secant of x factor that appears in both terms, and so we may write that we may factor out that factor of secant of x, and if we did, we would have secant of x times, let's see, secant squared x for the first term, secant x times secant squared x, of course, secant cubed x, and if we factor out a secant x here, we'd be left with tangent squared x. There are actually many other ways we could write this, because we could recognize that we might change secant squared x into some function in terms of tangent, some expression in terms of tangent, because remember, tangent squared x plus 1 is secant squared x, so we could actually write this as a tangent squared plus 1, and then we would have 2 tangent squared plus 1 in these parentheses. So I mean, there's different things that we can do, but I think that we'll be satisfied with this answer for this problem. Here we're asked to find a derivative. Notice this is a little different also because our variable is theta rather than x. And so rather than saying find dy dx, which x would normally be the variable, here our variable is theta, so we ask for dy d theta. Okay, well, the function is y equals secant theta times cotangent theta, and we're asked to find the derivative of that function. Now, our first thought in this problem is this is clearly a product of two functions, secant of theta and cotangent of theta. But a lot of times we get a lot of mileage by remembering identities, and old information goes a long way in simplifying a problem once in a while. So occasionally what I'll do is kind of look at see what I have. Well, the secant of theta is actually 1 over cosine theta, isn't it? So this is 1 over the cosine of theta, and the cotangent of theta is cosine of theta over sine of theta. And as soon as I've written that, I recognize that I'm going to have a reduction possibility. That is, this numerator and this denominator will divide to 1, and so we're simply left with 1 over sine of theta. So that thought is giving us a lot of mileage. Now, we could go from here and find the derivative by using the quotient rule, since after all this is a quotient. But we also can recognize very easily that 1 over sine of theta is nothing more than cosecant of theta. So a little previous trigonometry knowledge helps us rewrite the function y as just the cosecant of theta. And then it's a little easier for us to deal with the derivative because we have, of course, the derivative of the cosecant of theta memorized. dy dx then is the derivative of cosecant of theta. Now remember, the derivative of cotangent functions are always negative, so we have the negative of what? Well, it's the negative of the cosecant of theta times the cotangent of theta. So the derivative of the cotangent functions always are preceded with a negative, and they involve cosecant functions co-functions except for the derivative of the cosine of theta, or x, is just negative sine x. But here's our answer. Nevertheless, here's our answer. Okay, well, we'll get ready to look at the next problem. This is an interesting question and problem. Find the equation of the normal line to the graph of y equal tangent x at the point pi over 4, 1, and illustrate it graphically. Before we can even begin to work on this problem, we have to understand what a normal line is. So as we look here, the normal line at a point is the line that is perpendicular to the tangent line at that point. So for instance, if we look at this graph, okay, we want to know the normal line at the point that we have right here. So this is, suppose this is the point in question. So we're interested in the normal line at that point. Well, the normal line is this red line. That is, it's the line that's perpendicular to the line of tangency there, the tangent line at that point. So that gives us an idea of what we need to be thinking about. So let's kind of go back to this idea of how we calculate slopes, because remember, when we calculate the equation of a line, we need the slope of the line and we need a point on the line. So let's remember that if we have a point on a curve whose first coordinate is a, then the second coordinate would be calculated by putting a into the function. So let's assume we're talking about a function f. So the slope of the tangent line at a point a comma f of a is calculated, and let me refer to the tangent line slope with m sub t, is calculated by calculating the derivative of the function and then evaluating it at a. Now, when we're talking about the normal line, remember the normal line is perpendicular to the tangent line, and since the tangent line has this slope, then the normal line's slope, remember the relationship between perpendicular lines, they're negative reciprocals. So the slope of the normal line call that m sub n, would be the negative of the reciprocal of the tangent line slope. So what it would mean is we would calculate the derivative evaluated at the point in question, the a value in question, or the x value in question, and then our slope of the normal line would be the opposite of 1 over that slope we calculated. So we'll keep this information in mind as we go through this problem. Now once again, let's remember that we're asked to calculate the equation of the normal line. And as with any line, the equation of the normal line is we need a couple of pieces of information. First, we need a point that's on the line, and of course that's given to us here because it's the normal line through this point on the graph. And so the point we have that we're going to use is pi over 4, comma 1. Now the next thing we need to worry about is calculating the slope. Okay, so remember the slope of the normal line, and that's what we want. Well, first we're going to have to calculate the slope of the tangent line. And once we calculate the slope of the tangent line, then we'll say it's the negative of the reciprocal of the slope of that tangent line. Of course, the way we calculate the slope of the tangent line is we find the derivative of the curve in question, so we'll call that dy dx, and we evaluate it at the x value in question, and in this case that's pi over 4. Pi over 4. That didn't come out very clearly. So our job right now is actually to calculate this derivative and evaluate it. That's what we need to work on. So let's go over here and do that work. The derivative of y with respect to x, of course that's the derivative of the tangent function. That's the derivative of the tangent of x. Okay, well, but the derivative of the tangent x is secant squared x. So when we evaluate, here we go, we're going to take this and we're going to evaluate that derivative at x equal pi over 4. Which means we're going to evaluate secant squared x at the value pi over 4. So we've got secant squared of pi over 4. Then we have to remember that secant squared really means the secant of pi over 4 and that result being squared. Secant squared means calculate the secant of the value and then square that result. Well, I have sometimes a hard time remembering what the secant of pi over 4 is, but I do know that the secant is 1 over cosine. So this is really the 1 over the cosine of pi over 4, and cosine of pi over 4, and that fraction being squared. Now I'm making progress, I believe. So let's see, do we remember the cosine of pi over 4 is the square root of 2 over 2? So I have 1 over the square root of 2 over 2 being squared. And of course 1 over the square root of 2 over 2 is 1 times the reciprocal, 1 times the reciprocal of square root of 2 over 2, which is 2 over the square root of 2. And of course that's what I'm squaring. And so we're essentially just squaring 2 over the square root of 2. When we square 2, we get 4. When we square the square root of 2, we get 2. And so what we've come up with is that our slope of the tangent line is 2. Remember, dy dx here represents the slope of the tangent line. So finally we're interested in and finding what we're after, and that is we need, let's come over here, make ourselves some space. The slope that we're actually interested in is the slope of the normal line. And that slope is negative of the reciprocal of the slope of the tangent line, so negative 1/2. Okay, we've got the slope of our normal line, and we've got a point that is on our normal line, and so we put these together and say, okay, y minus y sub 1, which is our 1 value, is equal to m times, well, in fact, really, maybe I should remind you that we have y minus y sub 1 is equal to m times x minus x sub 1, and we're just filling in those values. So we have y minus our y sub 1, which is 1, is equal to our slope, which is negative 1/2, times x minus our x value of our point, which is pi over 4. And we begin simplifying here, and we see that we on the right side can write that as negative 1/2 x plus, because negative times negative is positive, and 1/2 times pi over 4. Well, 1 times pi is pi, and 2 times 4 is 8, so we get pi over 8. And then we need to add the 1 to both sides, so that we have y is equal to negative 1/2 x plus our pi over 8 plus the 1 that we've added to both sides. And I suppose we could combine these terms, but we'll be happy with this answer and this result, and stop at this point. There's the equation of our normal line. Well, we were also asked to illustrate this, this normal line. So let me show you what it looks like. Here's the equation of our normal line, y equal negative 1/2 x plus pi over 8 plus 1. And by the way, we could actually add these two numbers together by getting a common denominator and writing 1 as 8 over 8. Then we'd have pi plus 8 all divided by 8 as our constant. But it's normal, it's not unusual to leave our equation in this form. Here I've graphed the tangent function, y equal tangent x, and of course these represent the asymptotes that we know we have with y equal tangent of x. Here are our tangent lines, and of course this is where x is 0, and this is where x is pi over 2, and here's pi, and here's 3 pi over 2, and of course 2 pi, and so on. Here's negative pi over 2, and here's negative pi. But remember, we were supposed to find the equation of the normal line at the point pi over 4 comma 1. Remember, this is pi over 2. Halfway there is pi over 4. So this represents pi over 4, and these are the marks for 1, 2, 3. So this is the point in question, and so it's on this branch of the tangent function that we're drawing the normal line at. And of course, here's the graph of that normal line. We can clearly see a negative slope through that point. And the idea, once again, is this normal line is a way of thinking about a line perpendicular to a curve. So if we could blow that up right around, although it's curvy here, it would look like it's perpendicular at that point. This is an interesting problem as well as our others have been. A little different twist. Find a limit. We've been long gone from limits, it seems like, but here we're asked to find a limit. And we probably don't have an idea of where to start when we look at this problem, but let me give you a hint first that this is a conceptual problem. We're not actually going to go through and calculate. What we need to understand is, what does this limit represent? What does this, this expression, would a limit like this come from? And so the hint that I want to give you here as we get started is that we need to find a function and some value a. We need to find a function f and some number a, and find out that basically that this limit represents the derivative of that function evaluated at a. And here's what I mean. Let's look specifically. Let's remember that when we have a function f, and by the definition of the derivative, so our function is f, the derivative of f, remember, is defined as a limit. It's the limit as delta x approaches 0, of course, of f of x plus delta x minus f of x, all divided by delta x. Now, I don't know that we've discussed this before, but this is more or less this limit will be in terms of x. If we wanted to know the derivative at a particular value, at a particular number, we could calculate this limit not at a general x value, but at the number in question. Let's suppose that a is the number in question. So for instance, this would give us the slope of the tangent line to the curve f at the x value a. This is a specific value, and that's the same limit we have before up above, except we don't have the variable x in it. That is, it would be the limit as f of x approaches 0 of f of a plus delta x, and a is a constant, minus f of a, which just is going to be a number. See, f of a is just a number, not an expression any longer, all divided by delta x. And so we might see a relationship of f of a and the number 1 here. And of course, all of this needs to come from, we see the delta x, and so we begin to see things fit together. What we probably are going to need to try here is maybe make a guess that f of x is actually the tangent of x. That's the function in question. And a is actually the value pi over 4. Pi over 4. Well, of course, we see that tangent would appear when we find this derivative. And in fact, let's kind of carry this forward. Let's see what would happen. The idea is that we want our function to be tangent of x. And so if we were to calculate f prime of a, which is pi over 4, by the limit definition, that would be the limit as delta x approaches 0 of the fraction, well, let's see, the function f is tangent, and so it will be, instead of f of x plus h, see, let's get back up here, f of x, well, in this case, I mean f of a, pardon me, which is pi over 4 plus delta x, would just mean we replace this x with pi over 4 plus delta x. So that's the tangent of pi over 4 plus delta x. Well, it's awfully close in there, which is exactly what we have in this position. We have the tangent of pi over 4 plus delta x. And then we have minus f of a. Well, that's pi over 4, so it's f of pi over 4. All over delta x. Let's come over here. We see this part has appeared. That's exactly what we have here. The only question is, what about f of pi over 4? Well, f of pi over 4 is the tangent of pi over 4. After all, the function f is tangent of x. And the tangent of pi over 4 is in fact 1, isn't it? Because the tangent of pi over 4 is the same as sine of pi over 4 divided by cosine pi over 4. And that's pi over 4 is when the sine and cosine are both square root of 2 over 2. So we have numerator and denominator the same, and so we have a 1 value for the fraction. So what we have over here as we're calculating f prime of pi over 4 ends up being, let's write it one more time, the limit of delta, as delta x approaches 0, of the tangent of pi over 4 plus delta x minus, since f of pi over 4 is 1, it's minus 1 all over delta x. And this is exactly the limit that we're trying to find. So our limit is nothing more than f prime of pi over 4. So if we could calculate f prime of pi over 4, we would be done. But to calculate f prime of pi over 4, we need to know what f prime of x is. So we need to know f prime of x. Well, f prime of x is what? Let's see. Oh, okay. F of x here is the tangent of x. And so the derivative of the tangent of x is secant squared x. And so what we want to know then is f prime of pi over 4. Because that's the limit that we're looking for. And f prime of pi over 4 then, of course, is secant squared of pi over 4. That's the way we're thinking through this. And we ought to be able to calculate the secant squared of pi over 4. So we'll think through this a little bit. And okay, secant of pi over 4. Secant squared is actually, or secant is actually 1 over cosine, isn't it? So what we really have here is the 1 over the cosine of pi over 4 squared. And the cosine of pi over 4, we may recall, is the square root of 2 over 2. And so we have 1 over the square root of 2 over 2 being squared. Well, the square root of 2 over 2 being squared would mean we would square the numerator, which would give us 2, and square the denominator, which would give us 4. And so this is 1 divided by 1/2. But 1 divided by 1/2 is 1 times the reciprocal of 1/2, or in fact 2. So the limit that we were looking for, we found out was this limit we found out is the derivative of tangent of pi over 4. The derivative of the tangent evaluated at pi over 4, f prime of 4. So what we've discovered then is this limit that we were looking for has a value of 2. And that concludes this problem.